All right. Hey there, everybody. Just getting set up here. I think we've got a few people just rolling in, but otherwise should be able to get going here. Looks like somebody's already figured out the chat, but yes, just kind of ground rules for this conversation. Happy to take questions as we're going. I'll try to keep an eye on the chat and let you guys and kind of answer things as we go. I feel like that's kind of easier than bunching them all up until the end. But obviously, feel free to kind of ask questions whenever you want. We are here for deep learning on tiny micros. Share, and we'll get rolling. All righty. All right, so real quick, I'm Joe, family of 5, formerly John Deere. Now I'm leading a group called Dojo 5. We're focused on firmware excellence. Passionate about building great cultures, high-performing teams, and just lots of great firmware stuff. Dojo 5 is focused on modernizing firmware. We try to do immersive learning. That's where the Dojo piece comes from, and 5 is our foundation and family. Product and services company based in St. Paul, Minnesota. So real quick, we talked about, this is on tiny micros. What is embedded and what is a tiny micro? For purposes of this talk, computing device with a dedicated function is what we kind of call an embedded device. So generally, we're talking bare metal or RTOS in this case. We're talking less than 100 megahertz, less than a mega flash, less than, less than half a mega RAM. Just a pretty small device. We're not even talking Linux class devices. A lot of AI, deep learning, machine learning stuff has been done on like Raspberry Pi type of devices. Pretty easy, pretty accessible. But for the smaller micros, it's been pretty hard to get that up and running in a quick and easy way until fairly recently. And that's why I'm hoping to kind of show you how we can get up and running on that stuff. When we talk about what's a tiny micro now, not just a micro, but a tiny micro, I like to think about it sometimes in terms of power. And if you haven't looked at different power, you don't have a sense of where power ends up landing. So an EC unit might be 1 or 2 kilowatts. Laptop charger, 80 to 100 watts. Raspberry Pi's 5 watts. Your Roku's 3.5. Smartwatch might only be 26 milliwatts. And so you've got this very, and it's really that smartwatch or even less. TensorFlow Lite for micros is actually targeting less than 1 milliwatt devices. So these is pretty tiny little devices that can run on battery power. And so that's where we're trying to hit today. So I guess my issue, what I like to think about, I guess, or what got me motivated about this topic is that embedded development in a lot of ways is tragically behind, I'd say. Mobile and web guys have mature unit testing tools, amazing debuggers, one-click DevOps, real-time monitoring, lots of other stuff, and then also AI. And it was like, okay, and when I saw that, hey, this is available now finally for embedded, really like kind of low-level embedded tiny micros, I was like, wow, this is amazing. I think this is going to change a lot of, bring a lot of applications into a space where suddenly they're reasonable to run on these tiny micros where they couldn't really do it before. And really, TensorFlow Lite for micros has been the impetus of the ability to do this. TensorFlow Lite, as well as TensorFlow itself, born out of Google, and really, TensorFlow Lite is intended for the Raspberry Pi class devices or Linux class devices. Really think of your phone. And the first place it got used is wake word detection. So, version of this is already running on billions of Android phones. You know, when you say those two special words, I won't say because my phone will light up. It's a little neural network running in there, running TensorFlow Lite code. So Pete Warden and Raziel and some other folks decided, hey, there's not only is there TensorFlow Lite, but we want to start targeting even smaller micros. And they were able to target that internally and then open source it a little over a year ago. As I mentioned, targeted at less than 1 milliwatt devices. And it does have a limited API compared to like the full TensorFlow application API, but it's still, you can get a lot done with it, and it's kind of amazing what you can do. If you haven't done any deep learning, and I've got a big swath of people here, I'm not sure where people are coming from, so just kind of a high level on what we're talking about when we talk about deep learning, and really neural networks in this case. You've got kind of a path of steps that you go through, and largely they're the same, whether you're doing like a big, huge, there's a lot of talk this week about GPT-3, which is this Silicon Valley, like natural language processing and kind of generator tool. It's rumored to have, like hundreds of billions of information, or hundreds of billions of neurons in it. It's one of the largest, probably the largest neural network that's ever been brought into existence, rumored to take like millions of dollars to train. So whether you're talking a very large device like that, or whether you're talking a pretty, a tiny little device like we're talking about, the steps are largely the same. Step number one, you got to decide on what your goal is, and figure out, you have to kind of construct that goal in a way that a neural network's going to be able to understand. I've got a little kind of a portion of a neural network picture on the right-hand side there. And each of those circles is called a neuron or a node. And each of them takes one or more inputs and then produces one or more outputs. And they're traditionally represented as floats between 0 and 1. So you just got a real number, that can run anywhere. You can think of them as probabilities. In other cases, it's not really useful to think of them as probabilities. And in some cases, the nodes can have memory. In some cases, they don't. And so there's a lot of different ways that you can kind of put together these nodes to kind of help you build something that's kind of acting like a brain, or it's kind of doing all this deep learning stuff. You got to decide on the goal and figure out what am I doing. There's a number of different types of deep learning applications too, whether you're doing classification, which is something I'll be showing you, where you're given a number of different inputs and you want the system to learn how to decide, is it more like, number 1 or number 2 or number 3? Or you might be doing something that's more like predict whether this thing is true or not true about this picture. You might be doing something segmentation wise, where you're given an image and you're trying to find out, like, give me the bounding box of a person in this image. There's a lot of different applications that neural networks are already being applied to, deep learning is being applied to, and the goal, defining that goal, is really important kind of from the start, because it impacts numbers 2 and 3 pretty heavily. So number 2 is you collect your data set. Collecting a data set is another pretty, it's just, there's a lot of work involved in it, and you have to collect enough data, and it's a lot of data usually to get these models working, even on the tiny micro side of things. You have to collect, like say for instance, you want it to listen to audio and classify the audio in a certain way. You have to collect the audio, maybe you're just trying to decide, is some, maybe you're trying to do a predictive maintenance. Is my machine going to fail in the next, 10 minutes or the next hour or the next day, and maybe you want it to give a prediction of like, yes or no, we think it is, or we think it isn't. You likely have to collect a bunch of sounds of the device working normally, so that it can decide like, no, it's not going to fail, of device of the device failing. But then you got to think about the background noises that are there. You got to think about like, well, what if a second machine that's next to it is also running? Or what if it's a machine, you know, in a noisy environment? Or what if it's sometimes noisy when the workers are there, but when, you know, the shift change happens or something, then, you know, it's quiet for a little bit or something. There's a lot of different kinds of things that you need to consider in your data set, because basically if you haven't brought in the right data to train your device, it will get confused and possibly give erroneous predictions in those cases where it's presented with something it's never been trained on, never seen before. Once you have that in place, then you design your model architecture. And this is where there's a little bit of a black art and a lot of research that happens in the deep learning space right now. Typically, the best thing to do here is to go out to archive or some other, you know, research-oriented space and go find an architecture model that somebody else has done before. There are plenty of people who have solved a lot of these problems in the past, and so you want to make sure that you find an architecture and a model that somebody's proven out in the past, and then kind of tweak it from there. It's really difficult to kind of guess what's going to make sense by just kind of plopping nodes together. And as you'll see in that picture, I've got an input layer, a hidden layer. There's usually one input layer, one output layer, and then any number of hidden layers in between. And they can involve the same types of nodes, different types of nodes. And so you're really kind of looking for who's done this in the past, a similar problem, and then grab an architecture from them, start there, and then tweak it after that. So design doesn't necessarily mean design from scratch. It typically means go grab a model that's been worked on. Lots of researchers also have gone through a lot of the models and exhaustively tested, you know, a number of different architectures, and have found architectures that work much better than others. So you can kind of, you know, build off of their research. And then we go through an activity called training the model. So this is where we give the model some input. We look at its prediction that comes out the other end. We have some training algorithm that then, based on the results, twiddles with some weights that are used inside the nodes to convert, you know, map the input to the output value, and then run it again. And there's an optimization that happens, and we trying to kind of, you know, wiggle and jiggle all those weights towards a direction that gives us an optimal output. A lot of research goes in there too, but there are, you know, kind of some standard optimization tools that we just use. And then number 5 is really the main difference when you're doing this on tiny micros, is convert the model. So TensorFlow itself has a way to kind of serialize the model into a binary format that you can use, you know, both on the PC, but also in a tiny micro. But a lot of times those are way too computationally heavy for a embedded device where you'd want to, you're concerned about power or latency. You don't have a lot of CPU power to actually run the model once it's built. And so you can, without conversion, you can easily create a model that's going to take, you know, a couple hundred megabytes of RAM to run, or even gigabytes of RAM to run. You know, would take, you know, like possibly months or years to run on a little micro. And you know, obviously, and then chew up all the battery, and you'd be out of battery in 10 minutes before it even, you know, made a single prediction. So that's what the conversion piece does for us. And then really steps 6 and 7 are once you're on the micro, now you're running inference, which is basically, you know, make a prediction using the model, and then evaluate and troubleshoot it. So you know, point here being, there's a lot of steps to pulling together deep learning. Hopefully, you know, if you're familiar with deep learning on the larger devices, it's largely the same on smaller devices, at least using the TensorFlow model here. The hardware that I've got that I'm playing with today, and that I'm showing this off on, is an Arduino Nano 33 BLE Sense. If you end up buying this to play around with it, make sure you get the Sense version. There's a second SKU of this where they just depopulate a lot of the sensors, and that's a lot less useful for playing around with machine learning. Inside, it's got a Nordic NRF52840. This is a Cortex M4 at 64 megahertz, a mega flash, 256K of RAM. And it does have lots of cool peripherals. There's a color sensor, there's a microphone, there's accelerometer, and a few other things. It's a nice platform, and not only that, as you'll see, there's some nice kind of training and learning materials that kind of go around with this board. It's fairly cheap, and I think it exemplifies what we're trying to hit here. The Cortex M4 is pretty much the workhorse that I've been seeing of the kind of bare metal world right now. It seems to have hit a really nice balance between battery and power. You can get the M4F, which has a floating point on it, so it can do a decent amount of floating point. You can get enough processing power without chewing up a bunch of power, and so it's been a nice balance. And so I think this is a great example. And on this guy with optimized inference stuff, you can start thinking about running this on a set of AA batteries for a year or two. And this thing, depending on what your application is, how long it needs to wake up and everything, like it's now in the realm of possibility. Whereas before, just back of the envelope calculations, you're like, I'm going to be changing the battery every week, and it just kind of killed projects. So it's exciting. All right, so that is an Arduino device. We're going to be working a little bit on Arduino today, which is not, typically where I work, or a lot of more maybe professional embedded folks work, but it is, as you'll see, they're not hiding too much under the covers. I think it is a nice place to start. And then, as we, and you'll see that there's ways to kind of break out of that and get into maybe a more traditional environment where you're working in IAR, or you're working in VS Code with GCC makefiles or something. Like, you can get to a place where you can imagine this going onto a real device. But what's nice about Arduino is you've got the environment set up really quickly and easy for you, and it's you don't have to worry a lot about kind of those setup pieces just to kind of get to your first successful step. I've run through a lot of the setup here, but there's an announcement blog that I've got linked here too that kind of walks through it. All right, so I want to work through just a quick hello world is kind of our first thing to walk through. And to define the hello world, what we're trying to do here is get a very simple network that's going to allow us to predict a sine wave. So basically, it's predicting the sine formula. So we've got, as you know, sine takes one input, x, or sometimes you think of it as an x, and then it outputs another value, the sine wave, and you think of this plotted on an XY graph. And what we're going to do is train a function that will predict the sine wave, and then feed it x values in order. And then if it is able to correctly predict the sine wave, we're going to see an output from that go up and down. And then what we're going to do with that kind of sine wave output is then drive the PWM rate on a LED. So we should see kind of a nice like fade in, fade out, smooth fade in, fade out on the device. And of course, there's much easier algorithmic ways to do that, but it's just kind of an easy hello world for a machine learning process. So opening up this notebook. This is a notebook. Again, I've got these links out that the TensorFlow guys have put together to kind of help train on this. So this is something you can go back to. And this uses a tool called a Python notebook, or Jupyter notebook running Python. And it's kind of a mix between a wiki and code. And the code inside of this wiki page can be edited, but it can also be executed. And that's what kind of adds some power here, is being able to run this output and have documentation kind of interspersed. It turns out to be a really nice lab tool, and you'll find it a lot in the machine learning world. People use these a lot to just trade processes and tools and stuff. So this one ran right away. We're in Python here, and this is where we're going to generate the model and train the model in Python. So this is, we're not going to be training the model on the micro. We're training it in the cloud on big, fancy compute devices, and then those devices will present us with a binary blob that then we can plop into our Arduino and run some interesting things. And so this one, yeah, this requirement has been popping up on this guy. It turns out we don't actually need that requirement, so we're actually good without it. But it does pause the demo for a second while it's feeling out. There we go. So to start with, we need to create our training data. So this is like, if you were doing, something like take that predictive maintenance, you'd be sampling a bunch of audio. And in this case, though, we need to sample the sine wave and get a lot of samples from the sine wave. First, we're just setting up a random seed, and then we're using a high-level API that typically gets used in TensorFlow called Keras, and pulling in MATLAB. So I think everyone's kind of got the idea. We're creating a sine wave, and it's tough to see from this graph, but we haven't. This isn't actually like a continuous plot of a sine wave. It's a plot of 1,000 samples randomly distributed across the sine, between 0 and 2 pi. So these are going to represent our samples that we're going to use. They're basically XY value pairs, where X is going to be our input to the machine learning model, and then Y is going to be our output. We're going to add noise, and that does two things. It makes it more realistic, but it also prevents our model from getting overfit. And there is a danger that as you learn and kind of play around with these models, that they can get overfit. If you train them too long, if you train them with too clean of data, then they will start to take shortcuts, and they will get overfit to a particular set of data, and then they won't work well in the real world. So that's what this data, just Gaussian data that we've added here. And then we're going to split the data, and this is a fairly typical thing to do, is split your data between 60% training data, 20% validation data, and 20% testing data. As we'll see, so the training data is what we put into the algorithm to the training piece, and then we use validation data as something that the training algorithm hasn't seen, but gets run with each training step, because this training thing runs hundreds of times typically, or even thousands of times, and maybe even, depending on the size and the diversity of the data that you're using, you might even run millions of training cycles. But what we do is we use a certain percentage of the training data, but we don't, again, because we don't want to get it overfit, we want to understand how is it going to work in the real world. So we reserve some of the data that we've created to be validation data, and then final testing data as we go. So here we're splitting the data out. You can see we've got the blue data is the training data, the red data is the testing data, and then the gold data is the validation data. So we've randomly distributed our selection here too. And again, the randomness is important here, so the model doesn't take any shortcuts. But we've got, basically the majority of them are blue dots. There's some red dots and some gold dots. And then it's time to design the model. So we're going to use a really simple model, and we basically, simple model architecture, which is this Keras sequential model. We create a model, we add a layer, a dense layer, which is basically a layer of 8 neurons or nodes. They're using a specific activation curve, which is has to do with just kind of the mapping between the input and the output of each neuron. This is a very common one. And then they take one input, have one output. So it's a very, very simple neural network of only 8 neurons. And then we kind of make the final layer be just a single neuron, because we want a single output at the end. And that will be, we hope to train the model to make that, as value between 0 and 1 that represents our sine output. And then once you've built your model like we have here, we compile it. We're using an optimizer called Atom, which is the standard one. We're using a loss function, which is basically how do we want the optimizer to understand the error. And MSE in this case is just like the mean squared error of like we're telling it to optimize for how far off is it, either negative or positively, from the sine wave. And then the metrics are just mean average error. So we're going to see some metrics pop out at the end too when we actually train this. Once we're through that, we can train the model. Luckily, it doesn't take too long, but you can see, I'll get it. Oh, I forgot to hit run up here. So I didn't actually run the model. Now I've run the model. Now we can run training. And then while that's running, you'll see it doesn't take too long for it. This is a very small model, of course, too. But we're sending in the X training data, the Y training data, number of epochs, which is the number of cycles we want it to train. There's a batch size that it uses, as well as validation data, which gets printed out at the output, so that we can kind of track how the training is going. So that's basically, there's the training data and the validation data. So the validation data, importantly, is data that the model has not been trained on, but then we're independently validating it at each step. And you can see at each step, we get what epoch we're in, we get the loss, which is kind of like how far off are we on our, did we predict correctly? And then what is the mean average error for our predictions going in? And then the same two pieces of information, but then on our validation data instead of on our training data. So really we want the loss number to go down, and we want the mean average error to go down as well. And we want them to be roughly comparable for the loss as well as for the training as well as the validation data. If we're seeing that the training, the training data is good, is a high prediction rate, but the validation data is not, that means we've overfit. And we're great at predicting the training data, but we're terrible at predicting real world data. So we're kind of watching for that as well as we go. Now, in this case, basically what we're saying here is that about 17% of the data, it's a little weird because we're not doing a classification here, but about 17% of the data is kind of outside of our training threshold, what we consider a good match, and 18% for the validation. So I don't think we're in danger of overtraining or overfitting, but in this case, it's 16%. It's not very good, 17%, and we'll see here what the issue is. So here is mean squared error. We can calculate a plot here and even get a closer graph, which this is a little nicer. And we can see that after about 100 epochs, our loss has kind of plateaued. I mean, this is basically the system does a lot of learning initially, and it's getting better and better with each epoch, and then it kind of hits a knee and then it plateaus. And so we haven't really, it's unable to train much more at that point. And then, largely epochs 150 through 500 are not useful. It's not really learning anything from those, unfortunately. So we got an issue. How are we gonna, because not only that, but our mean average error is not great. We're kind of seeing a fairly large, 0.36 to 0.38. If you think of that in terms of like 38% of the value between 0 and 1, that we're predicting on the sine wave. It's we're struggling to get that working. We're struggling to predict the sine wave. So let's see what this starts to look like now, and it becomes very obvious what's going on. So here what we've done is in Python, we've used that model. Here's the blue is the actual training data that we've given it, or no, we used the test data. So now we're taking the test set, which hasn't been used at all prior to this. We remember we segmented out into training, validation data, and then test data. And so now we're throwing the test data in to see if this thing's any good. And the blue values are the correct values of the sign, and the red value is what the model has predicted. And so you can see that the models come up with some kind of piecewise, prediction for the sine wave, which, roughly approximate the sine wave, but is kind of terrible. You can see where our error is coming from. This isn't quite what we wanted. So we're going to train a larger model here, and that will help us. So in this case, we're going to actually add 2 hidden layers. So we're going to have 2, and then we're going to double the number of neurons in each layer. So we're going to 2 hidden layers, each with 16 neurons, and then still a final layer with a single neuron at the end because we need it to spit out that same value at the end. Then we can train the model. Training parameters are exactly the same. We compiled the model with the same optimizer, the same loss and metric values as well. This one does take just a little longer to train. It's a slightly larger model. But you can see already our loss function, we're down at 0.01. And prior to this, of course, we were at 0.16. So it's doing a much better job. Our mean average error is now at 0.08. And the same thing is happening in our validation data. We've gotten much better in our validation data. We're not looking like we're overfit. So now we've likely got a pretty good model and a trained model. And so we can draw the graph real quick of what that looks like. You can see that, okay, now not only did we come to a much better plateau, but it looks like we've got probably about the right number of epochs for how much the size of our network and the learning that it needed to do, right? It was still kind of, if we zoom in, you know, to those last couple, it's we're still learning, you know, kind of out till the 400s and maybe the 450s, but at about 500, it seems like we've pretty well plateaued. If we print out again, run the testing data against this new model, now we're much better prediction. You know, there's still a few little kinks in it. There's kind of a sharp edge down here, and this turns out slightly different every time I do it. But largely, it's trained pretty well on the sine wave, so we can say, oh, okay, that's probably a good model. And now we kind of get to so now we've kind of gone through those steps that I mentioned back here. We've been through the deciding on our goal, collecting the data set, designing the model architecture, training the model. Now we're going to hit the convert model. So this is the key part here, is that this is when we will start doing kind of micro specific stuff. They've got a TensorFlow Lite converter that converts it into, you know, basically a binary format. And then we can also do quantization, which is another optimization that's kind of unique for micro systems. So, you know, typically these models are built with floats all the way through, 32-bit or even 64-bit floats all the way through. And that's a big ask for a micro, especially, you know, and might be unnecessary in many cases for a micro if we're trying to optimize for battery or power or latency of the prediction. And so they've got a converter built in. In this case, we're going to convert it using one of their built-in ops that's called int8. So we're going to convert this into using 8-bit integers instead of the floats. And this has all compiled down, and then at the end, it's going to write out the model file, and we got a 2512 byte TensorFlow model then. So pretty small. It predicts sine wave. Now, you know, obviously it's you know, you can get a sine wave a little bit easier in a lot of ways, but that's what our neural network boils down to. You can also see that, hey, you know, at least comparing the models for size at this point, it just raw, you know, size as far as flash space or memory that you'd need to program this in. The float model with no quantization is at 2700 bytes, and so the quantized model is at 2500. It's you know, it's pretty small either way. It's not saving a lot yet. We'll see in a future one that it actually can save quite a bit. You could test the models now to make sure, hey, when we quantize, did I lose a lot of accuracy? And it's difficult to see in this model, but the light predictions and the light quantized predictions are X's, and they're pretty much bang on from the other ones. So in this case, with this model, really the floating point has not gained us much of anything, and we're pretty much you know, getting the same predictions regardless of the model here. So then we can generate our TensorFlow Lite from Micro's model. And this uses a tool called XXD, which basically is just taking that binary representation of the model and spitting it out in a C struct that we can, or array that we can just plop into a program. I'm going to pop up Arduino here and get the model going. So when you, and I guess I could do it here. So when you install, so I've got Arduino up here, and when you install the Arduino stuff for TensorFlow Lite, you'll get a new example, you know, basically example sketches down here, and they've got their Hello World one right here. So this provides a nice place to play with it. And it does come with some built-in model and built-in data. That's over here, the sine model data and the sine model data CPP and H. And here's their model that they tossed in there. It's no fun to use their model though, so we need to use our own. You know, they do unfortunately have this notebook spitting them out with slightly different types, so we have to fix up the types. But you'll see here, over here, now we have our model. So this is our model that we generated. it's an unsigned char here. So I just need to, and then we can plop that into Arduino. And we just need to make sure we have to change the name, and we have to change the type. So, and so we'll make this a const int instead of an unsigned int, and call it this, just to make this compile more quickly. And then up here, we need to match what they had to. So we'll make this a const unsigned char. Copy paste doesn't want to work for me. And then we need to call it the same thing too here. And sure, we can have the data align attribute, why not? So now we've got our program, and now we can compile it. Compile step takes a little bit of time too, so it's a good time for me to break here and just get it compiled. As I mentioned, if you look at the video here, they use the little BLE sense board. Pretty small little guy, runs on 3.3 volts, has this U-blocks module on the end. It was probably easier to see in the video, but inside of there is our tiny little micro. It's a Cortex M4. All right, so we've been able to compile it. We are using 20% of the space at this point, 52 kbytes. Not crazy, but a lot of that is TensorFlow. And I guess it's a good time for me to just kind of jump in here real quick and say that they're not hiding a ton behind the covers here. You still, if you pop into this hello world, we are pulling in TensorFlow Lite. We're pulling in all the TensorFlow header files. There is a decent amount going on here, even though it says, Arduino's kind of a toy, kind of prototyping area. And if you haven't used Arduino, the basic idea is it runs setup once, and then it runs loop over and over again. And so the nice part is you can actually see in this code, here's TensorFlow Lite, where we're actually grabbing our interpreter. Let's see, the way to think about this is that we've got a certain position along our X axes that we're calculating at first, and we're just kind of breaking down that X axis into a certain number of samples on the X, and then we just walk along that X value from 0 to the end. And then we plop that into this is how you place input data into the model. We've got one input that we are going to give it, which is our X value. Then we invoke the interpreter, and it runs, and it has a callback. So you don't actually see it handling the output here. I'm sorry. It has this output handled here, and then calls the handle output here. And then let's see, where is the output handler? Yeah. So then when the Y value is passed into the output value, we, if we haven't initialized it yet, this is Arduino speak for set the pin to an output, and then calculate a brightness, and then analog write is again Arduino speak for PWM. So we're basically setting the brightness of that LED based on our predicted output. So all right, without further ado, let's hook this guy up. We have to make sure that we are choosing the right board here. Now we've got the right port. There's my Nano BLE. And then you should be able to get the board info. There it is. We're connected up to the board fine, so I can program it. And what we'll see on this guy in, half an hour, but you could do it faster, I'm sure. It's going to program. And when it's done programming, we'll see that there's an orange LED on there, and you see now it's pulsing. And so that looks like it's a sine wave, but that is actually a neural network, running on the U-blocks module inside of that Cortex M4 and predicting the sine wave. So I think that's pretty cool, how fast you can get there now. And we've still got 80% of that baby left, so there's lots of other stuff we could put on there too, and obviously more complex examples. So then zipping back to the slides real quick, that's the hello world demo. And that gets us you know, kind of our, okay, now we think we got this figured out. Now what can we do next, right? I'm going to show off a quick tool. I'm not connected with them at all, but these are actually one of the guys that worked on TensorFlow Lite Micro, has gone to a startup. They're calling themselves Edge Impulse. They have a nice web-based tool. Honestly, I'm not sure what the business model is because you don't have to pay for it right now. I think it's probably engaging companies and you know, trying to get them more interested in TensorFlow Lite on micros, but they walk you through TensorFlow for the micros process. There's some really nice tutorials called Edge Impulse. So you know, they have an example about did I leave the water on, kind of like a water detection thing. And I thought, well, you know, in the world of COVID that we live in, let's think of something slightly different. So I put together a cough detection example. And so in this example, I've trained a model. The goal in this case is to detect, maybe in the entryway vestibule of a restaurant or something, is somebody coughing. And do we, you know, is that a signal then, or a sign, or maybe you use it in addition to some temperature sensing that you're doing to say like, oh, maybe this person needs to be, you know, some extra screening or something. And so maybe we just have to be aware and check out what's going on. And so that's my goal in this case. And I will, here, I'm pulling up the Edge Impulse stuff right now. So what I'm going to show here is a demo where I've collected a lot of data already. And we can kind of walk through what this does. They've got a pretty nice website. It kind of talks about connecting a device, acquiring data. One piece that don't have time to show today is they have a nice little app that you load onto your Arduino device, because the BLE Sense board is actually kind of a first-class citizen on this Edge Impulse platform. And they will allow you to connect up to your device, run an app on the device, and then it helps you sample data from the device. So you can see like, here's my Nano BLE when I built this example and connected it up. And so that client that runs on the device is able to sample audio in this case, and then got me my audio samples. And so in this case, I'm doing a classification, and I need to collect data and I need to label it. And so I sat for about 5 minutes, 6 minutes, and collected data and labeled it. And some of the data was coughs. Some of the data was just background of nothing happening. And background in this case could mean basically anything other than a cough that I want the model to recognize it. I took some background with me typing, since I'm by my computer. I took some background with me, you know, talking but not coughing. And then I took coughs with me typing, and coughs with background noise, and so that, you know, because you kind of have to train it on all those different scenarios in order for it to kind of understand what's, you know, have a shot at predicting these correctly. And so you can see that this is a nice way to kind of play with some more complex ideas around these TensorFlow models, you know. Yeah, and you can even play the audio here. And then what they call it a creating an impulse. I've already created it for you, and I've had trouble in the past with sometimes this doesn't generate the model quickly enough, but they, you create a model here, you create an impulse. They've got the neural network kind of set up for you. They've got an NN classifier. In this case, we're doing a classification. Is a background, is a coughs. Our network actually has two outputs. It's a prediction from 0 to 1. What's the probability that it's a background noise? And a prediction from 0 to 1. What's the probability that it's a cough? And so it spits out that for us. I already saved this. They also, you know, since we want to try to squeeze as much information as we can out of our audio data that we're training the device with, this actually breaks up the 10-second audio samples that I've given it into 1 second chunks and trains the model on those. And then it even overlaps, instead of breaking up into 10 chunks, it breaks it up into 20 chunks by overlapping the windows, or I guess it's probably 18. but it kind of it overlaps the windows so that it can squeeze as much information out of that data as possible, and hopefully the neural network, can learn that much better. The MFCC model, which is this Mel frequency cepstral coefficients model, which is, again, something out of a research paper that some folks put together that does really well at audio classification types of networks. It does have a number of parameters that you can play with to kind of tune it in. But largely, this is some of the art of training and getting a classifier put together. And then you have your neural net classifier, the actual neural network itself. And Edge Impulse is being slow at the moment. Anyway, under that neural net classifier link, there's basically then a number of more parameters that you can kind of play with to set up, like number of nodes in your network, number of layers, and kind of the size of the network to help you understand it. There is then, and then under that neural network classifier, that's where we can train the neural network. It looks like their website is having trouble. Luckily, I have this built already. But yeah, so you can retrain the model using information that you can upload to it. You can do a live classification where you can load the kind of the sampling application onto the Arduino device, and then kind of have it live classify for you. And then you can do model testing where you can see how is our model doing, and then deployment, which is where I'm going to jump to right now. I've already trained this model, and so you can see in the deploy step, they will spit it right out to a C++ library if that's where you want to be. They'll spit it out to an STM32Cube AI, which is another ST's AI kind of environment and IDE. And so there's a number of different ways you can export it, or you can have it just export for these. These are kind of like first-class citizens supported by this tool. And of course, here's our BLE Sense board. And you can have it spit out a whole ready-to-go binary. I spit it out as a library, and that's what I'm going to show off today. And so if I close this guy and then open up our examples, it ends up showing up here as an example. And then for whatever reason, it pops in a few other things that they do. But in this case, we want the Sense microphone example. And so I'm going to get this compiling right away because it does take a little time while I talk about it. But what this does is largely the same, and as what we saw before. There's a kind of a heads up setup, printout that happens, but then inside the loop, we're running a recording the microphone for 2 seconds. And then when recording's done, then we're running the classifier here. And then we're printing out the predictions. The result has a classification in it. And then it has if there's any anomalies, timing anomalies. But in the classifications, we've got the label provided. So what this is going to print out is it's going to say, like, did I think it was a cough? I thought it was a cough with this percentage of prediction, and I thought it was a background noise with this percentage of prediction. And so there's a number of other pieces here. The actual binary that's running the inference is buried somewhere in Arduino land. That isn't shown on these tabs, unfortunately, but if you dive into the code base, then you can go and see the demo. And you can see the model in the binary format of the model. This will take just a second more, and then it's I'll cough on camera, I guess, to show off the functionality of it. I would say that this model, the loss function is at about 16 or 15%. So it's not a particularly well-trained model, but it does a fairly good job, honestly, for what we've got going on here and the size of the micro. And I have no doubt that if I spent more time with it and tried to optimize the classifier, that we could get it, either a larger, slightly larger model, or some other things. I can show you too. There's a really interesting tool that they have in here. When you spit it out for Arduino, it'll actually say, so here we can actually see how big the model is. So this ended up being about 12, well, and they allow you to compare them. So in this case, we saved 10K in flash by going from the float 32 model to the int 8 model. The latency is huge difference. We can compute, and this is an estimation that they're making based on knowing things about this this platform. But we reduced the latency by an order of magnitude, down to 19 milliseconds, and then there's a decent amount of RAM being used, to be honest, for a larger, for something this size as far as a micro, but still very, very usable, and and this is doing a fairly complex task, detecting coughs in the middle of a random microphone sample. So it's kind of impressive how we get here. Let's see if we're done compiling. We are done compiling. Now we should be able to upload. And then once it's uploaded, we will pop open the serial port monitor and just watch it do some predictions. And I think this is a great time then. That's, well, I just have a couple more slides to go through real quick while we're waiting for that to load. So I think, kind of the punchline here is, can we have AI on tiny micros? And I think the answer is yes, we can. I hope we've inspired you to do something great with AI, or at least play around with it. It's pretty easy to get into and play around with at this point, and exciting to think about some of the things it can do. I'd like to hear, if anyone's done anything interesting like this before. Have I inspired any interest applications? Does anyone have questions about implementation, how we've done this? So definitely would like to hear all about that. I am doing a deeper dive on deep learning stuff. There's a August 15th session that's starting on Eventbrite, so check that out. Also, if you're interested in there's a 10-course module that we've got to kind of deep dive into these things in a self-serve lab type of style. So let's see, are we ready for the punchline here? Yeah, it takes a little bit of time. Oh yeah, with that, any questions, feel free to just toss them in the chat. I think other interesting things that I've seen with this, the BLE, oh yeah, here we go. We're gonna start programming here. But the BLE Sense board has a demo where they use the accelerometer and they detect different gestures. So there's like an L, an X, and a circle. And it, again, like you can work through the training. The Python notebook's available. You can do this, draw the circle, draw the L, draw the X, and get the training data. And then that's a classification, example. There are a couple of other good examples. There's one where it's a person detector where you do hook it up to a camera, and it's able to do some face recognition segmentation. And let's see, I think there's one more. Yeah, the micro speech, but that's similar to what we do. But their example with micro speech detects, they've got a pre-trained model that they spent like, I don't know, it was $1,000 or something training it, and gathered all the training data, and then it detects if you're saying yes, no, or background noise, or I think unintelligible. So basically something was said, but not yes or no. So that's kind of an interesting way that they go about it too. Lovely. Looks like this isn't programming. We'll try one thing here. Sometimes you need to pop this board into bootloader mode manually. Well, I think if there aren't any questions, again, feel free to have questions, to toss questions out. But if there aren't any questions, I'll stay on till noon. But that's our presentation today. I have a recording and the slides. Just hit me up on either LinkedIn or email. I had my email on the slide as well. It's just joe.schneider@dojo5.com, and feel free to, if you got any questions, thoughts, and additionally improvements to make this presentation better. I'm all ears on that. So here's the money. Here's it running a microphone. So here we see, yeah, just with me talking every once in a while, it's like 50-50, 60-30. So with me talking, it can definitely confuse it a little bit. And you'll see, yeah, sometimes you understand why it got confused, sometimes you don't. And there thought it's heard a cough, right? So there's still some mispredictions in here. I would say this isn't as well trained as you'd want it if you ran it into for production, and I'd say it's largely due to the size of my training data set, as well as the size of the neural network probably needs to be just a little bigger to do it correctly. But you can see the capabilities here, and it's not doing too bad even with a fairly limited training set. If I do a little cough here, I just feel like I'm going to the doctor or something when I do that. But yeah, so it seems like it missed that one. There we go. It saw like a pretty high spike on cough there. So it's, not perfect, but pretty interesting to see that this is, the capability is here and pretty easy to get going. All right, guys. Well, thanks so much for your time. Really appreciate it. Thanks for everyone and all of your interest in this, and feel free to hit me up afterwards as well. Thanks so much.